Hi, Sanish. Where are you based out of, Sanish? Can you hear me? Oh, your audio is not connected.
Hey, Sandeep.
Hey, Subodh, how are you?
I'm good.
Good. Did the project thing move? That McKesson?
No, I mean, just getting onboarded. So
Okay.
I think
Did you
Monday I'll.
finish those trainings?
Yeah, no, I don't have. I didn't had any access. I've raised a ticket uh, to get those access sorted out. I got an email today, so I'll check whether I get the access or not. The access to their portal, I didn't get it.
Okay.
I mean, I think it's just onboarding items which were missed out. So
Okay.
they said that I raised a ticket, they checked, they said that it'll get back to me in 2 days. Let's see.
Okay. No, I think that part, I think Vidya should be able to do it, isn't it?
I mean, I just raised the ticket and they're working on it.
Okay.
The IT tech team.
Okay. I'll just inform some more people. Okay. I'll just
All right.
inform. I just informed one May, the project leader.
Hmm.
Okay. And also the other data scientists in the team. So that
All right. I think on Monday, I mean, it just was Friday, right? So maybe Monday, once people are in, I'll get more help.
yeah. Sit with Sub for like go through his code.
Okay.
Yeah, go through the
All right.
entire code. Okay. So yeah, and understand the model. I know that you are not very comfortable with machine learning, but you are good enough right now. Okay, so do not worry. Just rest of the things are basically understanding the API of TensorFlow, training and all that. Okay, so yeah, I think it's more like job training. Since you have gone through the gradient descent, you'll be able to handle most of the machine learning projects. Okay. And that's the thing that I would like to tell everyone, that do not worry, just focus on, I mean, if there is a machine learning challenge, then take it up. You all can handle right now. Okay. And yeah, perfect. Okay. Wonderful. So let's continue from where we left, and I think that'll be fun. Okay. All right. Any questions before we start with differential calculus? Does quick question to you, all of you, is that does it still look scary, the differentiation and other differential calculus? No?
I mean, maybe I'll speak for myself, but it doesn't look scary. But in some cases, it looks like, very obvious. ये ऐसे ही होना चाहिए. But, to get the exact understanding of how exactly it is fitting into what we are going to do, the relationship between that, for example, we came to know because of differentiation, we know that, it will be used for loss functions or those kind of areas, right? So making the connect between the calculus part, the theory part, and where exactly it fits in doing the end-to-end project or doing the creating the model, that there is a gap there, at least in my understanding, right? Once we know that, then we'll be able to derive, okay, I mean, for doing differentiation, we get this, and this is how we actually use to do this. For example, the line function, right? We knew what the line function was, but then we used it to actually come up with a line which is closer to all the data points, right? So we were able, at least I was able to very quickly relate to it. So maybe if there is, once we do the theory part, which we're doing right now, how exactly we're going to use it or link it to the learning part, that might help. Again, that's my understanding. If anybody else wants to chime in.
Mm, mm, mm. That's a very good point. That's a very good point. Okay. That's a very good point. See, basically, the success of any class, okay, is two parts, right? Okay. And the most important part about machine learning, human learning, kids learning, everywhere. Okay. So the main core idea is this. Okay. That given the unstructured data, we figure out the correlations of various inputs and outputs. Okay. And then we basically take those and connect them together. That's the main idea, right? So, like, why, right? I mean, look at this way, that the way the whole science of prediction, I call it science of prediction or machine learning, whole science of prediction is this, that I am here, I want to survive, okay, right? So, right, I'll just make it very crude, okay, and me. What would take me from here to survival? Okay, for surviving, I need to basically have eat. Okay, for eating, I need to have food. Okay, so first have food, then eat, then survive. Now, so similarly, the thing is, we need to be able to come up with a hypothesis that doing this will give me money, so that, all right, so, okay, money, food, eat, survive. Okay, so each, like, doing this act, I will get money. That's my hypothesis. This is my first hypothesis. Hypothesis one. Doing this will get me from money to food. I can do this, right? Cook and everything. So that's my second hypothesis. My third hypothesis is that given food, I should be able to eat, right? And something, right? To cook and everything. So that's third. And then this is fourth. So every action and every possibility, right? What we do is we learn individual part, that me learning to make money, learning to make money. So I learned this. Then me converting money to food. That's my second hypothesis. And third is converting food to eating, cooking and everything. And then converting the eating to survival. Okay. So essentially, if you see, um, this is just very crude example I've taken. So similarly, I want to apply or solve with this class what you are here, right? And what you want to do at the end of day, you want to get a great job. Okay, great job. Okay, that's what you're trying to figure out, right? And how to get a great job? By learning to solve uh, ML problems. Okay, because the same thing would also be asked in the interviews. How would you solve them? These things and so on. Now, how do you solve the ML problems? Okay, and that's where there are like the courses, the practice, and so on. So basically we break down the full objective into subparts, and then we connect the dots to reach to our target. Okay, and that's how it is mostly. So, I mean, if you think about almost right, the neural network, these things, individual hypotheses are connected by different layers of neural networks, and in our case, these hypotheses we learn by training ourselves on subtasks and then reach to the final task. Now, coming back to your question, okay, that individually I'm able to figure out each part, but I'm not able to connect the dots. Okay. And this is exactly what my role is. That I want to make sure that you start here and then connect everything. Okay. That's why first we are learning like basic maths, like basic calculus. Now we learned about the basic calculus. Now we will start to apply it. Okay. And everything comes with, back to the life. And then you can see, I'm able to given a problem, I'm able to solve it. Okay. So that's the core idea. All right. So yes. So let me focus a little bit more about uh, you know, more about how do you apply each of this knowledge. Okay. So at every point of time, please keep on guiding me what to focus on so that I can focus on that particular aspect. And that's a request for all of you that guide me in terms of where should I focus. Okay. And many of the things look very obvious to me, but because I'm not able to remember how the things looked to me on the day zero of machine learning. Okay, because it has been very long time, I kind of forgot how it looked to me on the beginning day. Therefore, I kind of tend to skip things and go a little faster. Okay, so feel free to stop me at any point of time. Okay, I want you guys to just ask any question. Just ask any question. I'm quite used to answering every question. Okay.
Sandeep, I have how important is NumPy and Panda so that we can, because I was trying to implement something in NumPy and I am facing some issues, but I will resolve that. But how important it is to start NumPy and Panda before moving forward?
Basically, you don't have to memorize anything. Okay.
Hmm.
The strategy is going to be you should know what NumPy pandas do, what roughly functions are there. Just go through the list of functions, and that's it. Okay.
Okay. Okay.
NumPy pandas, how do you do that? Those things. Just go. We will anyway go through it soon. Okay. And then my request would be that don't have to memorize everything. Just have to understand the philosophy. That's all. Okay. Now, whenever you get stuck, feel free to ask ChatGPT or feel free to ask any of the available LLMs to help me write the code in NumPy or Pandas. They'll be able to do it for you. Okay.
Yeah. Yeah.
So utilize all of those really well. Okay. And when it generates the code and you are not clear about what each line is doing, just break down and test it out. Okay. Just break down, test it out, and then that will build an intuition that, this is what it does. Okay. This is what it does. And you basically can move ahead. Okay. Most important part to you is that you essentially it's a substitute. NumPy is a substitute to writing for loop. Okay. And it will take time, just like it takes time to get used to SQL. Okay. So just like we studied regex. Okay. First we studied Python. Okay. Regex. We also studied what else did we study? Python, regex, and Linux also we gone through briefly. And you should also take a look at SQL, Pandas, NumPy, okay, and so on. All right. The kind of questions people would ask you in Pandas and NumPy is that given a problem, how to solve it. Okay. If you are not able to remember exact formula or exact method of Pandas, just write the for loop. Okay. In the interview, if you're stuck, you're not able to get it done, just use the for loop part of the Pandas. Pandas also has something called map, and for each you can use that, or just go through just write normal Python for loop and get it done. Okay, it's completely okay.
Yeah. Thank you.
All right. And yeah, it is important. Okay, in simple words, it's important. You should know what is where. And but if somebody is asking you, tell me 5 methods of Pandas on how to do it, and they don't allow you to search, that means they're looking for typists, not problem solvers. Okay. So yeah, it's not on you, it's on them. It's the right. You don't have to worry about that kind of interviews. Okay. So yeah. And because anyway, such kind of interviews you won't be able to even qualify even if you knew every method of Pandas. There'll be something else that they will come up with. And even if you join such teams, your life will be hell. Okay. So the companies who are looking for Pandas function list, okay, avoid just such companies. Okay. Yeah, I think this is what I've realized, that if I'm interviewing somebody and I'm testing whether they can do data processing or do the data engineering for me, the way I do is that I ask them I ask them question, and I tell them that you use whatever tool you want and go with right. Go and search in Google. It's completely okay. Use ChatGPT, use large language model, but share your screen so that I can see what you're doing. It should not be you are asking somebody else and they are exactly giving you the answer. Okay. So based on that, I'll make up my mind whether the person is just blindly copy pasting the code from Stack Overflow or large language model or some other place, or they are really having an understanding. Okay. So have an understanding. You don't have to memorize the functions. Okay. And there we go. All right. Perfect. And where are we right now? We are in this notebook called this one. Close these. Quite a few things going on here. Okay. All right. So this we have all talked about before. Now we are at this. So everybody's okay with the concept of differentiation, this formula, or does it still look alien to you? F dash x is the first derivative of f, meaning how will the value of anything f will change as you change x. And what's f? F is a translation or a function that convert x into y. So when you change x, how much is y value changing, or how much is the output of f changing? That's what is the derivative or differentiation. And how do you quantify the change? You increase x a little bit, let's say delta x, okay? And then compute how much did the value of y change. The value of y increased this much, and we divide that, okay? This is just a, kind of a, disclaimer, okay? Just like you have disclaimer when you are reading a mutual fund policy, that, right, here limit is delta x need to be very small. Okay, that's a disclaimer. So this is sort of a disclaimer about this fraction. This divided by this. Okay. And that's it. So one of the use case we talked about is that given a equation, right? If we have to find a place of maxima or minima, we will compute the first derivative and make it equal to 0, and that will give us an answer. Okay. So and we talked about, let's take a couple of examples of the equations. Okay, let's take an equation, say 5x square minus 10x plus 20 or 2. Okay, so now question to you is, given this equation, at what value of y will, what value of x will y be smallest? Yeah, how would you compute this? We want to find out a place where this equation, okay, this equation, how do you, how did I write here? Let me just see. Okay, no, not like this. I had written somewhere yesterday, I'll say this one. Okay, begin. Okay. Will it work like this? I don't know. Oh, it worked. Nice. I just formatted it. Okay. Oh, this time it did not work. It has to be like this. Oh, I converted the cells data type to markdown and then it worked. Okay. Let me see how it works. Y slash equal slash. Oh, slash space means there is a space. Okay. Do we need space? I think we don't need space. Okay. Now this is better. Correct? Yes, this looks nice. I'll remember this. Slash begin, align, and align. That's it. If I don't do this, what happens? Nah, it did not work. Okay, so we'll remember this syntax, begin, align, and then we write this. Perfect. So what you see is, this is your equation, right? This is your equation. And we want to compute we want to find out where y will be minimum. Okay. So what will be the dy by dx? What's the dy by dx of this one? What is the dy by dx of x squared? Twice of x, correct? What's the dy by dx of this one? 10. And what's the dy by dx of 2? 0. So we get 10x minus 10. Okay. We know that the dy by dx is the rate of change of y would be 0 at the point where curve is rotating, meaning this curve at this point, you see the line, the tangent is going to be horizontal. Okay. Or you can say that this triangle, the perpendicular divided by base, where this is delta y, this is delta x, this is 0, correct? This is 0. Okay. So dy by dx is 0 at this point. Okay. At this point, it is 0. Okay. So if we equate it to 0 and find the value of x to be 1, that should do it, correct? That should do it. So we found out that for x equal to 0, dy by dx is 0. Okay, but we don't know, is it minimum or maximum? How do you find out whether this is minimum or maximum? We say dy by dx, and this turns out to be 10, which is positive, and therefore at this differentiation is basically at this point it's minimum. Okay, so
can you provide some examples of where these minimum maxima are typically used, which kind of problems?
yeah, so see, what are we trying to do in our normal case? Okay, what are we trying to do in our normal case? We are trying to figure out what is that slope and intercept for which the for which it is we are trying to find the slope and intercept for which the loss or the error is minimum. Correct? Error is minimum. We are trying to minimize our error. So that's a simple use case of dy by dx. We are trying to find the minimum value of error. Just like we are trying to find the minimum of y, similarly, this one. Okay. Now, there are many ways to do it. Okay. Here is a simple problem to all. Okay. Now, this is a rectangle. Okay. This is a rectangle. Okay. Now, okay, let me put a simple question to all of you. Question is this. There is a room of dimension 10 by 20 by 30. Okay. 10 is the height and 20 is the width and 30 is the length of the room. Okay. Ant is sitting in one corner of the room. It needs to go to another diagonally opposite corner. Which path shall it take? Yes. Okay. What is the smallest path shall it take? It cannot fly in the air. It can only go through the walls. Go through walking on the walls or on the floor or the roof. Okay. It can walk on the wall. It can walk on the roof. It can walk on the floor. But it cannot fly from one point to another. Okay.
Is it the shortest distance?
Yes. What is that shortest? Which path should it take such that it is the shortest distance? Okay. So almost every problem in maths in real life is all about optimization. Finding the shortest distance, finding the smallest path, finding the smallest this, finding this, finding that, finding the maximum of this, and so on. So most of the problems, even in machine learning, most of the problems are about optimization. Okay, so there are lots and lots of such problems. And let me give you another problem right now. So this is a problem that I want you guys to solve. There can be more than one way to solve a problem. Okay, and you will see that after you try to solve this question. Is the question clear to all? You can do it using geometry. You can do it using calculus. And yeah, you can find more ways to solve it.
I mean, I'll have to see how we can do it in code or so. But the answer to this problem is to the room, in the sense, convert the 2D to 3D, and then you have the point
It's a
where the ant
3D.
is.
3D. You have to
Yeah,
convert 3D to 2D.
yeah, it's a 3D room, right? So a cube, you open it up. So when you open it up, you convert 3D to 2D, and from where the ant is to where it has to go, just draw a straight line. That's the shortest path.
Good. Very good answer. I want others to also try solving it. That's one way of solving it. Okay. If I tell you that the speed on the walls, okay, here is another question to you as an extension. Okay, the extension of this question is this. Okay, your answer is perfect, by the way. Okay, and you have to figure out which way should you open the room. Okay, unfold the room. Okay, and that's a brilliant answer, by the way. Okay, the extension to the question is the speed of walking on the right. So speed of walking on floor to wall to roof is on these lines. Okay, the floor is 3, wall is 2, roof is 1. Okay, now you're given this, the ratio of speeds. Okay, that on the when ant is walking on the floor versus the wall, versus the roof, this is the speed. Okay, now you might say that why I'm asking these questions, this is a hypothetical question and it has no relevance in life. It is a lot of problems in industry revolve around such questions. So for example, I was designing the recommendation engine at InMobi, and I could clearly see that there is a correlation between showing the results upfront and we getting the feedback. So it's basically, it was very clear to me that it's a second-degree differential equation. Okay. And when you basically, in most of the cases, when you are solving the problem, if you are acquainted with the calculus, you would be able to come up with the solutions, come up with the mathematical, come up with the way of solving it. Okay, so you won't see a formula or maths behind many things unless and until you know the maths. Okay, so we learn maths and only then you will be able to see where to apply it. Okay, so a common question that I usually get is that this is fine, where do we apply such kind of optimization problems? Okay, our answer is almost everything. Okay, and I remember very well, I'll tell you very, very candid story. Okay, so in second year, my teacher, I wanted to stay back in a campus in IIT Roorkee. And my teacher I got a project from my teacher just because I wanted to stay back to get the hostel and everything. You need to have a project. And that's what I did. I got it signed by a professor that I'm doing a project from you. And he gave me a project. And the project was very simple. Given a temperature and a pressure, you have to tell the boiling point, melting point, and other properties of an element, such as copper, such as steel, and so on. You have to tell that. And you have the data about their boiling point and boiling point at various temperature, and all of these properties are there in the table. So you got to interpolate or extrapolate. Okay. Now, since I did not see it like a machine learning problem, I did not see it like an optimization, maths, and computing problem, I said, okay, I'm not interested in this. I want a computing problem, and this is a chemical engineering problem. It was not a chemical engineering problem. And I failed to understand this part because I had not really worked upon the machine learning. Okay, so coming back to it, the reason we miss out on lots of problems in our like lots of great opportunities in industry is because of us knowing the maths and science behind something, and that's why we miss out on lots of problems. Okay, lots of opportunities. Okay, and not the other way around. The other way, yes, I do agree that if you're working in a company and the company doesn't have a scope of a research or something, you end up not getting the work, which where you can apply some logic. But most of the time, it is our inability to see the problem. Okay, I mean, seeing the problem as an opportunity comes to those who understand it like a science. Okay, I can tell you, even like in a couple of my projects that we are doing right now, all of these things might look like that, hey, where do we, you know, like we were given a problem and I said, and they said that, oh, we need this, that, and when I looked at the problem closely and I said, we need to customize our own loss function. And bam, that's a, you know, that's the, that's a great opportunity. And before me looking at the problem, everybody was saying that these guys are not clear what they want. They say they are saying this, they're saying that, and it's not clear. Okay, so coming back to it, when you understand the science of it, you see the opportunity of applying and solving lots of problems. And when you do not know the science of it, everything looks, like a politics to you. Okay, and that's why I always recommend everybody to work on the math, get good clarity on maths. Okay, now let me just move on to the next question. Now, here is a next question to all of you. Okay, next question is that.
Sorry, Sandeep. What does the extension says, the speed of walking on the floor and all? We have that, right? Do we need to get the fastest path as well, or irrespective to the speed, the distance will be same, right?
Shortest path. Okay, fastest path. Shortest. Now it's good. Okay.
Okay. Got it.
Okay. So shortest, like in terms of time, like which path would take the smallest time? Okay. Now here's a question to all of you. Okay, be with me. This is a very important question. Okay. Question is very simple. There's a pond in which there is a person dying here, and you are here. You are here. Somebody is shouting help. Okay. This is the pond, and somebody is drowning in this water. Okay. Your speed of, running, this is the ground, and this is the water. Okay. So question to you is, to all of you is, what path will you take? Will you run till here and then go? Will you go like this? This is the path A. This is the path B. Or will you take some path like this, path number C? Your speed on the ground, okay? Ground is twice the speed of in the water. Your speed on the ground is twice that of in the water.
Run on the ground. Run on the ground.
Okay. So out of three paths I talked about, there is one path A, directly start swimming. Swim from wherever you are straight to the person who is seeking the help. Second is you run on the ground and go like this. Okay. And third is go here and take the cup. Yes.
So, I mean, we'll have to come up with an equation where x distance on ground and y distance on water with their coefficient, and figure out, where exactly the amount will be smallest. So like we did earlier, right? We'll have to figure out a value where, running on the ground will be, to what length we'll have to run to the ground so that it will give the smallest time, right? So
Yes.
diagrammatically, it looks like the B will give us that, but we'll have to come up with a.
No, I mean, are you sure that B will give us the shortest time? B is this: you go and make the full 90-degree, as much as possible you run on the ground, and then you go straight and swim. So this distance you're swimming, and this distance you're running.
And on the ground, your speed is double the water.
Twice that of water.
Sir, won't it be option A?
Option A, you'll straight swim. But your speed in water is like half of what you do in the ground.
So that's what I said, right? So we'll have to come up with a location where, till where we can run, and
You mean you will take some path C?
yeah, we'll have to take some path C where the time taken on the ground and time taken plus the time taken in water will be the shortest. So we'll have to come up with some equation where, that combination will be the shortest.
Right. Right. Okay. Let's do that right away. Okay. Are you guys with me on this question? Everyone? Is the question clear?
Yes.
Okay.
Yes.
So somebody is drowning in the water and seeking the help, and you have to reach in the shortest time. You have to reach in shortest time. The only problem is you swim, you run on the ground, let's say 3 times, not 2 times. I think 3 times is more realistic. You can run on the ground, say 3 times faster, and you can swim in the water at 1/3 of the ground speed. Okay. So if you take this path, the distance is shortest, but your speed is slow. Okay. So it may not work. Right. And right. And here, this one is the right way. So we have to find this distance X, okay, that you have to run in order to, and you have to run for X distance, and for this distance, you have to swim. Okay. So basically, the total time you will take, let's say you ran for a distance X, let's say this is from here to here, this distance is, let's say, let's call it D distance, and let's call this distance as Y distance, Y and D. Okay. So we ran, so the net time we are taking is right, X divided by your speed on the ground V plus, right? How much is this distance? Okay. Okay. How much is this distance? This distance is square of this and this. Okay. So this would be, okay, the square root of D minus X square plus D minus X square plus Y square. Okay. And we are saying D minus X. Sorry, D minus X. Sorry.
What is X here, Sandeep?
So we are saying that, okay, I don't know from where. What we are saying is from here to here, we will run x distance. We are assuming some variable x, and we have to find x. Okay, we have to find that x distance till for how long we should run on the ground, and after which we will swim. Okay, we have to find that x distance. Okay. So how would you do it? We basically start here and we say, okay, for x distance, we are running on the ground. And for this distance, d minus x square plus, let's say, y square divided by v by 3. Okay. So this is my, this is the distance. Okay. Now we are saying, okay, we are saying dt by dx has to be 0. Okay, dt by dx has to be 0. Okay, so this is how much? 1 by v. This is how much? When you differentiate it, you get 3 by v and twice of d minus x square plus y square. That's the formula I have memorized. Okay. And then we equate it to 0. And we solve for x. Okay, we solve for x and that's it done. Did I confuse you guys? No? Okay. Yeah. Yeah.
We are confused. I am
Okay.
confused.
Okay. Okay. Let me go slow. Let me go slow. Okay. So you're here at this corner. Somebody is dying in the water and seeking the help. You have to reach to them really, really fast. Okay. You know that you are really fast. You are 3 times faster on the ground as compared to water. So you ran for X distance and then you took this. So this is your distance and your speed is, let's say, V. So total time you ran outside is X by V, right? And then from here, you took this. How much is this? If the total distance was d minus x square plus y square, and this is y. We are assuming that this is y, this is d. So d minus x, this length, and y square, that's the hypotenuse. And we are saying that my velocity in the water is 1/3. So time taken in water, time taken to swim from here to here is this much. Time taken to go from here to here is this much. Okay. And right, so the time in the water is going to be 3 times. Okay. And so this is my formula. This is the formula that I came up with. X divided by v, the time on the ground, plus
Path C, right? Path C. For path C, we are writing this,
yeah,
right?
we are
Okay.
we are doing only path C because path B or path A, neither of the extremes are good. Okay, neither of the extremes are good because path A, though the distance is shortest, but my speed is very slow, 1/3 of the actual. Okay, so and path A, path B is again, since here the total distance is actually pretty big. Okay, and hence I chose some other path in midway. Are you with me? No? Okay.
Yeah, the first part is clear now that
Okay, let's just go slow. Let me rub everything off. Okay, let's just leave it here and then go slow. Okay. All right. So I would make it, can I make it a little more cleaner? Okay. All right, let me make it much more cleaner. Okay, now, okay. And why I'm spending my time on this is that you should be comfortable at creating these equations when needed. Okay, differentiation is a tool that helps you optimize, that helps you finding that minima or maxima. Okay, differentiation is a tool that helps you compute the rate of change. Okay, and the quality of rate of change is the rate of change is 0 at minima or maxima. Okay, and the rate of, like, second derivative of rate of change, okay, is positive at minima, negative at maxima. These are the qualities that we know. And since there is a full table of, you can look up the formulas of all the possible functions and everything, people have computed for everything. So you can algebraically differentiate, or you can find the rate of change of things if you know the formula. Okay. And then you can use the differentiation like a tool. Okay. Now let's take a look at this. So this formula is okay with everybody? Are you guys, do you think I made a mistake here somewhere? Subodh?
No, I mean it looks okay. But I'll have to, I mean, relook at this.
The other way could have been that instead of assuming X here, we could have assumed theta. Okay. And then we could have used theta to do all of that. Okay. Never mind. So let's start.
Just one doubt I have, Sandeep. Like one equation may have both maxima and minima, right?
Yes.
So then if we are making it 0, then we'll get either maxima or minima.
No, you might get multiple values there.
Achha.
Okay. You might get multiple values. Like if I say, right, x cube minus 3. Okay, 3x square. Okay, this is my formula, right? Right, and I can different. Let's say this is y equal to, so dy by dx is going to be 3x square minus 6x equals 0, right? And then the answer, like there are how many solutions are there? It has multiple solutions. First solution is x equal to 0, and second solution is x equal to 2. No, it's equal to square root of 2. No. I take out 3, you are left with 2. Yeah, it's x equal to 2. Yeah. Okay. So you can see you have two solutions to this, x equal to 0 and x equal to 2. Okay. When you take the second derivative of this one, okay, you see that this comes out to be 6x minus 6. Okay. When you put x equal to 0 in this, you get minus 6 at x equal to 0. And when you put 2 here, it comes out to be plus 6 at x equal to 2. So at x equal to 0, it is maxima. And at x equal to 2, it's positive, plus 6.
Positive means minima. Yes.
This is minima. Okay, and this is maximum.
Yes. Got it. Thank you.
Got it. So,
Yes.
yeah, sorry to mess up this. I'll just try to show you. X cube minus 3x square, right? What was that? X cube minus 3x square. Okay, let's just see on here. All right. If your equation is y equals to x cube minus 3x square. Okay, so you can see there are two formulas here. So what we calculated was at x equal to 0, it was maxima, and x equal to 2, it was minimum. So our calculation was right. You see that? Okay, so without looking at the graph, we were able to solve it. Are you guys with me?
Yes.
Okay.
Yes.
All right. So basically, that's a clever way of solving this problem. We could also solve this problem by other means. Okay. You could basically do this. Okay. We take, let's say, initial point here, or here. Let's say 4 or 5 points. And then you start doing the gradient descent. Okay, the chances are for some of the points that you chose in the beginning, you will end up here. Okay, and for this and this, you might for this point, you might keep on going to infinity, right? Forever. All right. For x less than, if you chose x less than 0, you might keep on going up, right, down. Okay. So essentially, the gradient descent is not great if you have multiple minimas. Okay. The gradient descent is only great for the situation where your curve is like this. Okay. Where whether you start here or here, you will drop down till this smallest value. Okay. Now, coming back to where we were. Ouch. I have removed everything. Now I have to figure out. Okay, let me see. Will it revert? Yes. Okay. I'm removing this part, the one that we did later. There's no way to just bookmark these. I'll start using some other tools. What's a good tool that you guys recommend for drawing in the class? I saw Xkelly draw. Okay. Okay. So this formula is okay. Now, our job is to find that value of x for which time is minimum. We want to find out that value of x where the time is minimum. Because both extreme, this extreme and this extreme of x, what is the minimum value of x? Minimum value of x is 0. Maximum value of x, d. And somewhere in between, we have to find out the location. So one way is you can do a bit of hit and trial. Okay, let me choose x equal to x equal to d by 2. Okay, and then see is it good enough. Okay, and we basically have to do the back and forth. Okay, so one way is that. Other way is that we do the differentiation way. If that solves it, okay, if we are able to solve that equation, good enough. If we are not able to solve that equation, we will use the gradient descent way. They will try increasing x a little bit if it is going good or bad, and we accordingly swing the x back and forth. Okay, so that is another way of solving it. So we can use the gradient descent, all right, in this formula, as well as we can use the normal differential calculus. Okay, so there are multiple ways of solving the optimization problem. First one, the gradient descent one, we have already used. The second one is what I'm using, like talking about right now. So dt by dx, okay, x divided by a constant. So differentiation of x is 1 by v plus this again a constant, so I'm just leaving it v by 3. Okay, numerator. Okay, so I know that square root of x, if you differentiate, it becomes 1 by 2 and the entire thing goes in. So differentiation of square root of x is how much? 1 by 2 root x, correct? Is that right? Anybody remembers? No. No?
Yeah, it's same as the power thing, right? It's the 1 by 2 power. So 1 by 2 power comes here and x raised to 1 by 2 minus 1. So it will
Exactly.
be minus
This.
1 by 2.
Perfect. Okay. Let's just, yeah. Perfect. That's correct. You remember it. Which year did you finish your 12th?
Oh God, it's long back.
Very nice. That means you understood it. That's why you have not forgotten. Okay. 1 by 2. The whole thing comes in the denominator. D minus x square plus y. And the differentiation of this one is twice of d minus x. times -1. Okay. All right. So that's pretty much. And right, we are saying this should be equal to 0. Okay. Multiply everything by v and also 3. So we get 1 plus 3 and 2 get cancelled out. Okay. 3 times d minus x and -1. So I'm just putting it -1 here, divided by square root of d minus x square plus y square equals to 0. Okay. Are you guys okay how I reached from here to here? Okay. There's a high chance that I'll make a mistake, so you guys have to keep an eye on it. Am I making sense, everyone? No. It has been really long time for all of you, right? Looking at these big formulas. Okay. All right. And then basically using this, we can simply say, okay, d minus x whole square plus y square equals to 9 times of d minus x whole square. And this is 8. And I would say that, right? So, okay, so you can see here, here we take the square root of both sides. So y by 8 square root and x equals to d minus that. Okay. So something like this. Okay. So something like this. So if you, here in this case, if you run for this much distance, okay, if you run for this much distance, right, this much distance, okay, if you run for this much distance, x equals to d minus square root of y minus 8, that means you would be able to reach in the shortest time. Okay. Are you guys okay with this? No?
Sandeep, in the above numerator, d 2 into d minus x and -1, from where this -1 came?
Oh, because it's d minus x, right?
Oh, okay, okay. You have integrating. Okay, okay. -1. Okay.
Okay.
And
All
for
right.
y, it will be considered as constant, right?
Yes.
Okay.
Okay. It's a chain rule. Okay. You can actually derive all of the chain rules using the simple limits theorem. Okay. You can just use the limits theorem to do the derivation of all of these parts and then put them together. So we found, by the way of strategically solving this equation, we found the value of x, and that's how we would save somebody. Okay. Now the question is, would you have time to do it? Okay. So the thing is, maybe in this particular case, it won't help. But when people were dropping bombs and you have to save yourself, all of these calculations were really, really useful. Okay, the entire differential calculus, entire of the computing was used for in this manner to save yourself. So essentially, finding that minimum time, smallest path, smallest money to pay, smallest cost, highest temperature, lowest temperature, and so on and so forth. All of these problems that you see in maths, chemical engineering, civil engineering, most of them revolve around the optimization. Like, for example, if you have a big pipe, if you cover it with insulation, it emits less heat. But at the same time, when you put the insulation, you're increasing the size or the surface area of the pipe. And you basically are increasing its surface area. And as you keep on increasing, you basically reach to a point where it starts to emit. And this is where, again, differentiation come into play. You say, okay, for X amount of insulation, this is my formula. You differentiate it, put it to 0, and that's it. Bam. Okay. Similarly, you will study in one chapter called there was this great model called XGBoost. If you know XGBoost, if you have not heard about it, I'll tell you the story. So before the neural network, the algorithm that won all the competitions on Kaggle was XGBoost. Okay? XGBoost. Okay? And before that became the thing, right? So XGBoost was winning it. And the secret behind XGBoost was this simple optimization. Okay? Simple optimization. So the person who coded it, the person who actually coded it, just used the differential calculus. So, and the way he did was, if you increase the weights, okay, in a model, if you increase the complexity, right, the model starts to memorize. So he added a penalty and so on. So basically, his point was that his cleverness was that what is that optimum number of weights or optimum number of complexity to add in the model so that it neither overfits nor underfits. So what is that midway path? And that's where he used the differential calculus again. What is that midway path? What is that optimum path in between? Okay, neither too slow nor neither all water, not all ground, somewhere in midway. Okay, so finding that optimum point where you get the maximum return is something that you use the differential calculus for. Is everybody on this so far? Okay, the actual problem that we are going to solve is much more easy. Okay. Yes, Nitin,
so I don't understand how are we applying differential calculus in the last question. Could you please explain that again?
Where? The one that we just solved?
Yeah.
To save a person?
Yes, yes.
We applied, right? Differential. So your question was?
I don't understand like how are we using, like where are we using the differential calculus to calculate the
we did, right? This
process?
one, we did a lot of calculation. This one. So we computed the time. We assume the distance to be x, that we will run for x distance. We will run for x distance, then we will swim to save this person who is drowning in the water. Okay. We calculated how much time it will take on the ground and how much time it will take while we are swimming. So we'll run for this distance, swim for this distance, and bam. Okay. And I will save it. So, but we don't know how much is x. So this is my time. This is the formula we calculated. Then we said dt by dx should be 0. So we calculated dt by dx and equated it to 0. And we found this formula. We found that if our distance x is equal to d minus square root of y by 8, we will be able to save this person. Got it?
Okay. Yeah, got it.
So this is where we are applying. We applied one, calculated dt by dx using the differentiation formulas, and then we equated to 0 and then solved it there. Okay. So yes, this is how we apply. Now let's get back to the question. This one is way easier question now. Okay. This one is a way easier question. Let's go back to remember this formula, this one. Okay. So what we did was this. Okay. 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 Yeah. So let's say we have these data points. Some data points we had, right? 1,8. Okay. We had, remember, 1,8, 2,11, and 3,16. These were 3 data points given to us. Okay. I think we have mentioned those here. 1,8, 2,11, and 3,16. Okay. These are the 3 data points given to us. Okay. Are you okay so far? So we are given these 3 data points, and we have to find out what is that best fitting line through these data points. Okay. So let's assume that best fitting line is y equal to mx plus c. We assumed it. We don't know how much is m. We don't know how much is c. We have to find out that value of m and c, which is the best fitting line. Okay. Now, so what we did was we defined an error. Okay. We said, okay, my error is the square of all the differences in prediction. Okay. So when we put in the first data point, my error is how much? So my model is saying m times 1 plus c is the prediction for y, and actual is 8. So I subtracted 8 from predicted, and that's the difference in the predicted versus actual, and I squared it. Similarly, I put the second data point. I said for x equal to 2, how much is the predicted value? So 2 times m plus c, that's my predicted value, and 11 is the actual value. So how much is the error? This minus this, and I square it so that negative doesn't cancel second one. And also the emphasis is on the individual value. Now, the third one, I did the same way. For 3, I calculated as per my model. This is the model that I'm chasing. I want this model to be perfect. Okay, I want it to have the minimum possible error. Okay, minimum possible error. Now, I cannot make this error 0, but I can find the minimum value of this error, or I can find that value of x, that value of m and c, for which my error is minimum. Please note that here, we are not after x or y. We are after m and c. We are going to find out that value of m and c for which my error is minimum. Okay, we are given multiple x1, y1 data points, and based on that, we calculated error. Are you guys okay with this formula so far? All right.
Yes.
Okay, so I'm going to, all right. Can't I paste an image here? No? Is there a way to draw here? I hate this thing. Okay, looks like there is something called this. Can't I paste or something? Nah, it's not working. Never mind, I'll just try to do something else. Okay. Okay, let's do it. Is there any other way of? Yeah, this is way better. Okay. So this is power. Okay, this is power. All right. So this is my formula. Okay. And yeah, this is the formula that I'm trying to differentiate. Okay. Is there a better way of doing it? Yeah, this is better. Okay. So yes, right. So what I want to do is I want to find the minimum value of E. Okay. I want to find the minimum value of E. How would I do it? Everyone? One way is that I would basically take this from here, okay, and put it in this. All right. Oh man, it's not letting me plot this. Okay. Okay. So one way is that I would do the hidden trial. Okay. Say, for example, this seems to be good enough. Okay, I'm just doing hidden trial. Okay. Now I can just keep on doing that again and again. It's nice, not bad. Like that. Okay, just the gradient descent way, I can just keep on tweaking them, observing which way it's going down, and I just keep on minimizing that. Okay, one way is that. The other way is, right? Other way is that I do the differentiation. Okay, so what I'll do is I want to find those values of M and C for which the error is minimum. Okay, so what do I need to do? We will do delta E by delta M.
Delta M and delta E by delta C. Right.
Correct. You're absolutely right. Yes, thank you. And okay, let's do that calculation. Delta E by delta M is equal to twice of M plus C minus 8 plus 4 times of 2M plus C minus 11 plus 6 times of 3M plus C minus 16. Correct? So 2 times 2 comes out, so that's 4. 2 times 3.
I didn't get this calculation. Can you just explain?
So when we are differentiating with respect to m, we are saying c is constant. We are treating c as constant. Okay, let's take a look at the first part when we differentiate. When we differentiate the first part, it comes twice of whatever it is, so twice of that, and then multiplied with differentiation of this one. What is that? If you differentiate m times 1 by with respect to m, that becomes 1, and the rest becomes 0. So this times 1, right? Are you guys okay? Twice. Okay, remember that way we did y equal to okay. So the way you can think of it is this. Okay, if we were given this in the form of y and x, y equal to, let's say, x plus c minus 8 whole square. Okay, so what we could do is we could say y equals to capital X square, and capital X is x plus c minus 8, and then we can differentiate, and that's it, right? So yeah, okay. So we are doing a differentiation, right? Not clear?
First term I got it. How is the second term 4 then?
See, twice of 2m plus c minus 11 multiplied with 2 more, which is coming from here. So if you see y equal to twice of m plus, let's say I'm just putting constant square. So how much is dy by dm? 2 comes ahead, 2m plus c, right? Multiplied with, when you differentiate inside, 2. Got it? No. The chain rule. Pratik, your voice is not clear. It is like muffled.
I think we should remain with m cross 2 plus c minus 11 because we directly differentiating it, not putting it as a common term.
We just it will be constant. This is the constant. I actually did not understand. Did anybody understand? If somebody understood, could you repeat, please?
No, we could not understand.
Pratik, could you type the question, please? Voice was very muffled and noisy. Are you there?
Yes, I'm there.
Okay. So you were saying that why are we not taking the c minus 11, is it?
As we have differentiated, x square equals to 2x.
Yes.
So we remain with x. So for the m square 2 plus c minus 11 should be remain there, and then we should differentiate inside of it, like chain rule.
Yeah, that's correct. That's what I've done.
M square is not there, like m square plus c minus 11. It should be there. And then
No, this is m times 2. This is m times 2, not m to m square. This is m times 1 plus c minus 8. This is m times 2. This is m times 3. So this is 2m actually. This is essentially, I think this is causing confusion. Let me just see if I can make it simple. 1m, okay. This is m, 1 times m. This is 2m, okay. This is 2m, and this is 3m. Okay, now it makes sense to you?
Yes, sorry.
Okay. So let's just calculate this, right? We'll say dE by dN equals twice of m plus c minus 8 plus 4 times of 2m plus c minus 11 plus 6 times 2 into 3, 3m plus c minus 16. And we'll say that this is equal to 0. Okay. Similarly, we would say dE by dC. Okay. dE by dC is twice of m plus c minus 8 plus twice of 2m plus c minus 11 plus twice of 3m plus c minus 16 equal to 0. Now you got two equations in m and c. Can you find the value of m and c from it? So for each weight, if you have like 100 weights, we will have 100 equations. We'll differentiate error with respect to 100 weights separately, and then equate them to 0, and then calculate the weight value of those weights. Okay. Right now we have only two things to find out. We have only two weights, m and c. Okay. Are you with me?
The weight means the dimensions, right?
Yeah, like the things that we have to find out in the model. Right now we are trying to find out the intercept and the slope for the line. We might have like more parameters, and we just have to find out those. Okay. All right. Looks okay, everyone? No? Yes. All right. Now I can simplify these equations. Let me simplify these equations. Okay. And yes. Okay, so first equation, let's simplify the first one. Okay, 2m plus 8m plus 18. Okay, so that is 28m, 2c plus 4c plus 6c. Okay, 2c. Did I make my sense here? 2 plus 8, 10. 10 plus 18, 28. Okay, 2 plus 4, that is 6. Okay, that is 6. 6 plus 6 is 12. Minus, okay, help me out, please. Somebody who is good at calculations. 16 plus 44 is how much? 100 plus 10. I'm sorry, 50 plus 10. 16 plus 44 is 16 plus 44 is 50 plus 10 is 60 plus 96. Okay, 60 plus 96 is 96 plus 60 is how much? 156. We could actually just divide the entire thing by 2, right? We have to just unnecessarily wasting all our energy in this. Okay, so 2, 2, and 3. Okay, I'll just have to do it again. Okay, so 1m plus 4 plus 1 5 5 plus 9 14 m. Now c is 2 plus 1 3 3 plus 3 6 and minus, okay, 22 plus 8 is 22 plus 8 is 30. 30 plus 48 is 78. Is that okay? 78 equals 0. I can again simplify it. 7
6c, right?
C, correct. Okay. Are you guys okay with this? I simplified this whole thing into this equation. And then I'm doing it for the second one. And that's pretty much. So I can divide entire thing by 2. So 1m plus 3m, 4m plus 2m, 6m plus 1c, 2c, and sorry, 1c, and what I'm doing, 1 plus 2, 3 plus 3, 6, c, 1, 2, 3, 3c minus 8 and 11, 19. 19 and 16 is how much? 19 plus 16, 19 plus 10 is 29, and 6 is 35. Is that okay? Yeah. That's the equation we got. Okay. How would you solve this equation? Just subtract from the first one. Okay. So we get m minus 3 equals to m minus 4 equals to 0. So we got m equals to 4. That's okay, right? Yeah. And how much is the c that we will get from it? C equals to 35 minus 24 by 3. Okay, is that right? So if I put m equals to 4 here, so this becomes 24. 35 minus 24 is this, and this comes to be 11 by 3. So C is 11 by 3 and m is 4. Are you guys okay what I did here? I just want you to walk through the entire calculation. Okay, but we had already written one formula, one code. Remember, if you remember that, for solving these equations, I had already written one algorithm to do that equation solving. Remember that? So we could just use that. Okay, I have done here the same calculation. You see that this calculation I have done. And looks like I messed up somewhere. Okay, this seems to be a better one. And then when we have these equations here, okay, once we framed these equations, dE by dm, twice of this, twice of this, twice of this, we got this equation. Okay. Okay. We did correct, right? 6 and yeah, m equal to 4. That's right. Is that what we solved? M equal to 4 and C equal to 11 by 3. Yes, yes. So we actually got it correct. So our solution was also right. And we had written this, the code. Remember this code, which takes equations and solves them? We use that one to solve it. Okay. And there we have it. Are you guys okay with this, what we did so far? Does anybody want to volunteer to repeat what we have done so far and why we are doing it? Why we are wasting all of your valuable time into this? Everyone?
Sandeep, what was the value of C? It was 11.
11 by 3.
Okay.
Which is 3.667.
Okay, got it.
Okay. All right. Can somebody volunteer to repeat in some other words so that everybody is on the same page? Everyone, please.
I can try.
Yeah,
I can try. So we have 3 points, 1, 8, 2, 11, and 3, 16. So we want to fit the best line possible. We are predicting that is y equal to mx plus c. And how can we fit the best line possible is by minimizing the error. So we know how to minimize the error. So how to minimize the error, we need to get the best possible M and best possible C.
Yes.
So for getting the minimized M and C values, minimized error with M and C value, what we'll do is we'll take the derivative of E with respect to M and derivative of E with respect to C, and we will equate it to 0. So we have the formula that E equal to EM plus C minus 8. So we put those points 1, 8, 2, 11 and 3, 16 into that error formula. So we have that equation. We will find the DE by DM and DE by DC values, and we will equate it to 0 so that we will get the minimum of M and C values. So when we calculate that, we get two equations. For DE by DM, we'll get one equation which will be equated to 0, and DE by DC, we'll be equating it to 0. We have two equations. We'll solve those equations and we'll get the value for M and C. So for that M and C is where the error will be minimum.
Yes. Yes. Perfect. 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 All right. I think I messed up. Run all above. Okay. So yes, you got it absolutely right. Okay. So is everybody clear what we did here?
So why do we equate it to 0 when we are doing del E by del M?
Yes, we equated this to 0 because on the graph with respect to M, if you think about with respect to M, there is some value of M on which that graph is turning, error is turning like this. Okay, so we are computing that rate of change with respect to M because at that value, the rate of change would become 0. On the minimum value, on the minima of the curve, the rate of change becomes 0 because that it becomes horizontal. The rate of change in Y with respect to X becomes 0. That's why to find the minima, we'll say DE by DM equals 0. Are you with me?
So this would only work for straight line equations, right? Would this work for higher degree equations?
No, it won't.
Okay.
If you have more columns, if you have more, instead of only one X, if you have X1, X2, X3, right? Then what we will do, instead of saying Y equals to MX plus C, we will say, let's say we have, we have a table of data. Instead of only X1, X2, it has X1, X2, and Y. Okay, so let's say this is, you have some data, and this is your label that you are predicting Y. So you will say Y is equal to some constant, let's say AX1 plus BX2 plus C. Okay, so this is your equation. Okay, you will put in all these data points to compute the error. Right, you'll compute the error in terms of A, B, and C. What you'll do? Delta AE by delta A equal to 0, delta E by delta B equal to 0, and delta C by delta error by delta C equal to 0. I would express my error in terms of predicted versus. I'll fit in this value, and using this, I'll calculate the error. Then calculate the error. If there are 100 data points, there will be 100 terms in this. So, and then, but my equation will always be here 3 because we have 3 parameters to find out. Now I'll get one equation from the first one, second and third, and then I'll solve it, and that's it. Got it?
Yeah, thank you.
So How many equations do we need to solve? If you have got n number of columns, how many equations will be there? If you have, here there are 2 columns, so there are 3 equations that will be formed, right? And if there were n equations, how many, sorry, if there are n number of features, like we call them features, the x1, x2, right? So if there were n, x1, x2, x3, x1, like xn, how many equations will you have to solve?
n+1.
n+1, right? So if you have too many features, you will have too many equations to solve. Are you with me, everyone? So number of equations is not a function of how many data points you have. Instead, it is a function of how many features you have. Correct? And does anybody remember, if you have n equations and you have to solve those n equations, what's the complexity of solving n equations? Yes? Does anybody remember? No? Solving m equations takes order of m cube. Okay? So if you have too many features, this method is extremely slow. Okay? This method is extremely slow. All right? Okay? So this method is called the normal equation way. There is a formula for it, but I don't want you to look at the formula. Okay? I don't want you to look at the formula. And that's pretty much. Okay? So I don't want you to memorize the formula, but you can just take a look at normal, or we can say least squares method. Okay? So here is the method. Okay? And you can take a look at this one. Okay? And yeah. Okay, so this is how you basically, solve it. Okay, this is how you solve it. You basically compute the inverse of it. Computing inverse is equal to solving the equation, and that's it. Okay, whatever we just did, the same thing has been formalized as symbols. Okay, and that's it.
Sandeep, how taking the inverse is solving the equation? That I didn't get.
Basically, inverse is what? Inverse is essentially equation solving, right? So if you think about it, okay, when we have, okay, it's a good thing that you asked this question now, because now we are ready for it. Okay, I'll come back. I'll get back. So
this is like matrix inverse and transpose, right?
yes.
How,
yeah, I'll explain to you that soon. Okay. So is everybody clear that we solved the equations and we got the answer for M and C here? This one? No? Yes?
Yes, Sandeep.
Perfect. And any doubts on this before I go ahead and answer the question with respect to inverse and move ahead? Are you guys okay? Everyone? Please feel free to ask the questions. Okay. I have tried my pace to be slow, but I know that most of you are looking at the maths after a very long time. And yes, math is a little sore to the eyes. I know that even though I'm pretty good with maths, still when I read through, let's say, a quantum physics book, I feel sleepy because I'm not comfortable with the symbols. Okay, and it basically just naturally or instinctively has a tendency to put me off and move me, and I tend to lose focus. So I very well understand it. So feel free to ask right away.
So Sandeep, it's naturally like even sometimes when we see a lot of formulas, I thought it is even I'm quite comfortable with maths, but still I get I will get sleepy when we see a lot of like different
Yeah,
characters and giving
yeah,
equations.
yeah, 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 yeah.
Sandeep, with the
So it's not only
calculated
problem with me.
MNC, we calculated one MNC, right? What was the error, minimum error that we got? Like in the graph you were showing, right? We can go and check there, right?
Yeah,
What was the
yeah.
minimum?
So some error, okay, I can just set the value to 4, and this was how much? 11/3.
Yes.
Okay, this one. Okay, so the error is 0.67.
Okay.
Yeah. All right. So yes, the symbols are usually the problem. There is, symbols have in different maths books, people use different symbols. And it was nowadays the symbols are still actually easier for square, for equations, and for derivative. But in olden times, it was a big problem. Okay, like the first Fourier's algorithm was solved long back, but people could not interpret those symbols, and therefore during World War II, a lot of things could have been solved if we could have done the fast Fourier, like if we could decipher those symbols. Okay, and that was very weird because people did not understand the symbols of each other. So symbols are pain, and it's easier to read a plain English than read symbols. I remember reading one of the books by, I think, Roger Penrose, or one of the authors, and his publisher told the writer that, hey, don't use any symbols in the book. Just write it in plain English. If you use symbols, nobody's going to read it. And that's so much true. That's so much true. That's why in that videos, as long as I have shown, instead of symbol, I've shown Apple icon. Instead of saying A, I've shown Apple. And instead of saying B, I've shown bananas. Okay. So till that point of time, everybody's clear about, and everybody stays focused. And the moment I start showing X1, X2, and all that, everything just like people start losing focus. So yes, it's very natural. It's very natural that we have hard time reading through the symbols. Okay, and that's very natural. So yes, given that fact, I want everybody to give me feedback. Is there a doubt how we solved it? Yeah, I'm waiting.
Sandeep, I have the doubt on the question that you have given. You first initially you gave one question, right? 10 into 20 into 30 is the dimension, and you have to find the and problem. So can you just draw it and show what needs to be solved there? Like from when you draw the pond and you showed that, we understood the problem. But
Okay.
here I am a bit confused. What needs to be solved? I'm not able to understand.
Okay. I will try, but I think I'll confuse you more. Okay. Yeah. Let me draw a 3D room. Okay. This is the room. Okay. It's a cuboid. Okay. It's a cuboid, and the cuboid is not this. This is nothing to do. 10 by 20 by 30. 10 by 20. Well, let's say this is 30, 20, or let's say 10, 20, 30. Okay, so this is 30, this is 20, and height is 10, right? Now, ant is sitting on one of the corners, say this one, okay? And it has to reach to just opposite corner, okay? Either it could basically go till here for some distance, then walks till some distance here, and then walks on the roof. Or it just goes to this side somewhere, and then goes up to here, and then goes like this, or goes like this. There are multiple ways to go. Okay, so the question is, what kind of path shall it take? You have to tell like which path, or let me make it even simpler. Make it simpler. What is the smallest time it would take to reach here? What is the smallest time that it would take to reach here? Okay. Smallest time, or just give me the smallest distance. That's it. Just give me the smallest distance. What is the
Sandeep,
smallest?
the ant can go to diagonally opposite or like diagonally, like if you start from the start point and
Okay,
go
you are
straight
saying
line
that it
on the
will
20.
go on this one wall like this diagonally and then walks like this.
Correct. Yeah.
Yes. But how you are so sure that this is the smallest path?
Based on the total distance, we'll decide. No?
Yeah.
Ideally, we have to calculate the multiple distances, and based on
Yes.
which is the shortest distance, that we.
Yes.
Okay.
Yes. Yes. See, it's very clear if you just go by corners, like first go to this corner, then climb up, then go like this. This distance is the longest, right? But if you go somewhere diagonally, like here, again, you're going to the corner, so this is not really optimum. You have to go somewhere like here, from here to here, from here to here, like that. Okay. Okay. So definitely, what I feel is that it would the way will be like this. Okay, right. There are multiple strategies to solve this puzzle. Okay, and you can, without calculus, also you can solve the strategy that Subodh was suggesting. That okay, you open this like a matchbox. Okay, and then once you open it, you will look at it like a big triangle, a big rectangle, and then you just go from here to the diagonal. That's it. But that problem becomes harder when I put forth this. Okay. All right. Those who are still wondering the pond problem where you jumped into the water, right? Remember the pond problem? I just forgot to tell you guys, if somebody is here, and then what we did was we said, okay, we will run and then swim. Okay. So actually the light, okay, you remember the light formula? What is it called? The refraction formula. That actually light figures out this. Okay, when you go from lighter medium to denser medium, instead of going straight forward, it goes a slightly like this. So it tilts. So it tries to find that path. It tries to find that path that takes the shortest time, because for light also, traveling through water is slower. So it tries to go through the path which is the shortest. Okay, so light is doing this calculation every moment of time. Are you with me? So that refraction, if you differentiate it and do that, you will be able to derive that refraction formula. Okay. So
when you say it tries, always successful.
So basically, on the quantum level, what light does is it travels through all paths, but the path which are not the shortest, those paths take infinitely big time, and therefore those are not successful, and it basically takes the shortest path. Okay, shortest time path. At the quantum level, it tries all possible ways, but those paths which are not shortest, those words die down, and therefore it never reaches that. So it reaches through the way we calculated. Run for the ground on the ground, and then so it basically tilts that way. Got it? Yes. So trivia is that equation that we studied in childhood about that refraction that can be derived using the things that we discussed today. Okay. So yes, whatever we discussed, even though that looks trivial, but it's fairly advanced when it comes to the maths and the physics of it. Okay, the things that we studied, they have a tremendous applicability in physics, and the machine learning, and in other sciences as well. Okay, are you guys with me? All right. Before so let me start moving to the next question. Next question was yeah, what was the next question? The next question was with respect to this. Okay, so whatever you see this formula means the same thing. This inverse means solve those equations. This xt dot x is basically coming up with those equations, multiplying the coefficient with the powers, and then you have this. If you see what we did here, okay, look at this, right? So, okay, 2 times this, 2, right? 2 times 2, 2 times 3, like that, okay? So, essentially, this whole thing is all about that. Okay, this whole thing, if you see, my loss function is y times xb. Okay, so xb is nothing but when your capital X represents 1, x1, x2, xn. Okay, so I put all of these in one bracket. Okay, and instead of saying y equals to, okay, so let me again put it. So remember, first equation was y equal to mx plus c, correct? Right? We could write it like this: y equal to m, comma, m and c, and then x and 1. Okay? So this is like a dot product. So this, I mean, the way you can represent this, saying that, okay, my one vector is n comma c, other vector is x comma 1, and I can say this is, let's say this is my the weights vector w, and this is my x, so I can say w and x. W is an array of weights, and x is basically my feature values along with one extra added to it. Are you okay? So y equal to mx plus c can be converted into y equal to m and c times x and 1. Okay, this is basically a dot product. Okay, that's a definition of dot product. Are you okay? No. Yeah.
Yeah, got it.
Okay. Now let me so if this is clear, right? Now if my equation was like, let's say we had multiple columns, x1 and x2, right? My equation will be y equal to some constant. Okay, let's make it simpler. W0, W1, X1 plus W2, X2, right? So instead of M and C, I'm saying W2, W1, and W0, right? And I'm saying here further, this thing is a dot product of W and X, and where X is basically equal to 1, comma, X1, X2, and W is equal to W0, W1, W2. Okay, so my Y is equal to W times X. Okay, so everybody okay so far? So whatever we did with the equations, I want to move it to the vectors so that you get acquainted with the linear algebra without having to go through that linear algebra book. Okay, so I'm slowly moving it. So I said, okay, instead of dealing with one number at a time, we will represent a bunch of numbers together using something called a vector. Here, capital X is one vector that contains bunch of numbers together. W is another vector. When you say dot product, it means this gets multiplied with this, one gets multiplied with W0, X1 gets multiplied with W1, X2 gets multiplied with W2, and then we sum it up, and then we get this. So W0, W1, X1, W2, X2. Okay? It's the symbols. Just get acquainted with the symbols. That's all. Okay?
Yeah, got it.
Right? Now, here in this example, instead of saying W, he's saying beta. Okay, so let's say you have X1, X2, and Y. Okay, Y is what you are trying to predict. So Y will be, let's say, instead of W0, I'll just say beta 0, just to make sure that we are on the same page here. Beta 1, X1, beta 2, X2. Okay, so we have to find those values of beta 0, beta 1, beta 2, for which the error is minimum, is closer to the actual value. Okay, so we also, to differentiate between actual and predicted, we put a cap. So this caret at the top means this is a predicted value, this is the actual value. The data set is having 3 columns and multiple experiences, and we are saying this is the actual value Y, and here Y caret is my predicted value. And how are we predicting? We are saying there is some constant beta 0, beta 1, beta 2. Those are the things that we have to find out. And we are further making it like simpler. We are saying Y caret equals to beta, or let's say capital X times beta. Okay, dot product of these two. And capital X is equal to 1, comma, X1, X2. And beta is equal to beta 0, beta 1, beta 2. Okay, are you guys okay with the symbols? It's only the symbols that are different, okay? That's the only thing that will freak you out. That's why I want to spend good time on these. Are you guys okay? Y caret is equal to X, this and this. Right? There's a silence, and I'm very afraid of this silence. Omdat, Parimita.
This beta 0, beta 1, beta 2, all these are like the M and C value that we had solved, right?
Yeah.
And so that into the that variable X, that will be the dot product. That's what you meant, right?
Yes. Okay. Now, look at it this way. Okay. So whatever we did here, but one value at a time, we're going to do this here, right? So let's take a look at here. So what we are doing, we said, how much is the error? Okay. How much is the error? Error is equal to predicted minus actual whole square, and we will sum it up. Okay, instead of summation, we are saying sigma. Okay, so instead of saying this is one error, and so on, we're just writing it like a summary format. We are saying sigma. Sigma means sum all the errors, all the squares of the errors. And individual errors will be y caret, which is predicted value of y minus actual. Okay, so predicted y minus actual y whole square. Okay, and then this essentially is being written like a little bit more cryptic way. Okay, so it's just a cryptic way of writing it. If you write it in English, this will look really easy to you. Okay, so here we are saying L as in loss. Okay, loss. Beta means loss is a function of my data and my parameters. Okay, how much is that? It's the total. You see this double this. Okay, and there's a square. It means it's a summation of the square. Okay, summation of the square. I'll come back to this symbol again. Okay, it's the distance from origin for this vector. Okay, so you subtract it and then you square it and sum it. That's it. That's what it means. Okay, now how do you square a vector? You basically, if you have to square something, okay, what you do, let's say you have to square 1, 2, 3. Okay, what do you do? What do you do? Instead of squaring it, what you do? 1, 2, 3, and you make it vertical 1, 2, 3, and then you do the multiplication. And remember, how do you multiply two matrices? Take the row, multiply by column. So X times the X transpose. So whatever is your vector, transpose it, that becomes vertical so that you can multiply it. That's what is going on here. Okay. So those who are wondering about this maths, this is essentially exactly what we did manually, one thing at a time. The same calculation has been generalized for more than for any number of parameters. Okay, that's the calculation that's generalized. So this is nothing but multiplying this value with itself. So we transposed it, made it horizontal. I think by default it's vertical. We made it horizontal, multiplied by itself, we got it. Okay, and then he has just opened it like this. Okay, opened it like this. Now he computed the gradient. The way he has computed it, just like what we did, compute the gradient. The gradient turns out to be twice of X transpose Y plus twice of this, and so on. And then when we equate it to 0, we get an equation like this. Okay, equation like this. And which means that what we need to do is, to calculate B, we have to basically, we got an equation in terms of beta, all the weights, and there is a constant, and we have to solve it for beta. So he has just said, okay, do the inverse of it. Okay, and that's it. And doing the inverse is nothing but, okay. So, all right, let me take a step back. Okay, let's say we are given 3m minus 2c equal to 11, m plus c equal to 5. Okay, and this is the equations that we are giving. All right, now we can also write it like this. We can write it like 3 minus 2, 1, 1, and we can say m and c equals 11 and 5. Right? So When we want to convert the equations into like symbol format, we can basically the definition of matrix product comes from this. Okay, matrix product is take the row, multiply with the column, so it becomes 3m minus 2c and equal to 11, 1m plus 1c equal to 5. Okay, so these equations are represented like this. Okay, so and you can also say that this is nothing but, let's say, some x data set multiplied with beta equals to y. Okay, same thing, as in instead of saying this equation, we are saying like this, x beta equals y. That's all. Okay. Now, in order to solve this equation, what people do is, okay, I want to find the value of beta. Okay, so what I want to do is I want to multiply the right hand side with x inverse so that I get this. Okay, and the way people do is that they essentially figure out the way we solve equations is that that's how the inverse is calculated. You insert one column and you eliminate variables, you keep on eliminating the columns, and that's how you calculate the inverse. Inverse is nothing but just eliminating the values. That's all. Okay. And yeah, that's how you do it. So I can
Why do we call it inverse?
Inverse means that, okay, there is some value of inverse x we are multiplying such that this value becomes 1, okay, and we can find out the value of beta. Okay, so solving equations is what we call computing inverse.
So what is the inverse of this 3 minus 2, 1, 1, that matrix? How can we calculate the x inverse of
Just
that
like the way using the elimination method, you can start eliminating C, first M and then C, and then calculate the value of M and C. And that basically, some form of that is what is called inverse. Okay. So you essentially, okay, how should I explain? Okay. All right. Like, okay, I think I'll just do it some other time. It's already 12:43, but basically it's exactly like equation solving. Okay, take a look at how do you do the inverse of a matrix. It's essentially the way we solve the equations. That's all. You just basically you put on the right hand side 1, 0 and 0 and try to turn this thing into one like a diagonal, like upper diagonal matrix, and that's how we do it. Okay, it's essentially solving the equations the way we manually eliminated one variables and all of that. The solve method or inverse matrix method is the same method. Okay, that's what. So you solve by computing the inverse is essentially solving that equation to find betas, and that's what we have done here. Okay, so you can take a look.
Earlier we had done some exercises for solving equations.
Yeah.
So can we just use that here?
Yeah.
When we say
yes, that's exactly what I have done here. You see this?
okay.
Yeah, we can just use that. Okay. All right. That is much more simpler way of looking at it than going through this thing. This thing kind of messes up everything. It basically takes up, right? So basically, whatever we are doing here is actually just done here, just that it's different symbols. Okay. Inverse is about solving the equations, and that's all. And everything else is just exactly what we have done. Okay. So here, first we computed actual minus predicted whole square, then we made it simple, and then we computed the loss with respect to each of the M and C, and then equated it to 0. Then we got some equations, And once we got those equations, we solved it by computing the square, and that's how we calculated all the weights. Okay, same thing what we followed there is also done here. Okay, just that symbols are different. Okay, so that's pretty much. And yes, this is called the least squares method. This method is good, but the more number of columns you have, the more number of weights you will have, and therefore the order of feature, which is, let's say, n cube. If n is your features, you'll have n plus 1 weights to solve. And if you have n plus 1 weights to solve, the equation solving is cube, right? So it'll be O(n) cube. So approximately the complexity of this method is O(n) cube. If you have too many columns, this method is horribly slow. Okay, gradient descent wins any day. Okay, so people hardly use this method. This method is good if you have a small number of columns, a small number of rows, you can just use this method. But gradient descent is the method of is the choice of everybody. I wanted to cover this so that you are clear about it. This method is also not applicable in a situation where this is not square. If it is something else, this loss function is not like this, and it's like really complex. When you do the differentiation, it comes out to be really complex thing, and you cannot solve those equations. Here, these equations were basically simple linear equations, so we were able to solve it. But if your loss function changes and becomes really complex, you cannot solve those equations, and therefore this method is not used. This method is only used in least like in the mean squared error. Okay. All right. So again, if right.
But Sandeep, how we will decide the based on feature we shouldn't be use least square method? Any
If basically the simple thumb rule is don't use it. Okay. All right.
Oh my God.
Yeah.
Okay.
Okay. If you're, because this is like applicable in very small scenarios, and it doesn't make sense. Okay. So people do use it, but gradient descent is much superior. The only thing is in gradient descent, you have to have all the optimizations, you have to keep running it multiple number of times, you have all hyperparameters to tune. In this, you don't have any of that. Okay, you just basically simply fit it. Okay, you just have to only solve equations. So you have, when the problems are very simple, and you have to do linear regression, you use this, otherwise you don't use it. Okay.
Sandeep, what is this hyperparameter? It's the eta value only that we are using.
Yeah.
Gradient descent, right?
Yeah. Eta value in like number of epochs, how many times you should run that loop, and as well as what should be our initial values. Those are all hyperparameters.
Okay.
Okay. Those are the things that you have to decide. The things that you have to decide and gradient descent cannot find out is called hyperparameters. The things that gradient descent figures out, like M and C, we call them parameters. So parameters versus hyperparameters. I hope you're clear. So weights or parameters is the same thing, and we will use them interchangeably. But hyperparameters are those which the system cannot figure out. You have to figure out. Okay, you have to do hit and trial there. Okay, so that's the only advantage, but most of the time people end up using the gradient descent with everything. Okay. All right, so I would want everybody to be comfortable with gradient descent. Even if you are not comfortable with least square method, it's okay. But I would want you guys to be super comfortable at the gradient descent. Okay, so right, if you did not get this, it's okay, because you can code it up. Whatever we have done manually, you can just code it up. right? And then solve this, okay? And be comfortable, all right? Most important is, even if you did not understand these symbols, it's okay. You if you understood this, what we have done in this notebook, that's more than enough. You'll be able to be able to think in terms of algorithm. You'll be able to think in terms of solving problems, okay, rather than stuck in the translation. Okay, so go through this notebook. I would request everybody to go through this notebook. It is really, really helpful. Okay. And yeah, I have tried to avoid too much of symbols, too much of that overload of linear algebra, but without losing the purpose. Okay, the purpose is very simple. We have to figure out those values of weight for which our loss is minimum. That's all. You can use a linear algebra, this package, that package, or you can use pen and paper, or you can use some other mechanism. You can use quantum physics, quantum mechanical model. You can do hundreds of more optimization. You can use biological ways of figuring out those values of weights and parameters, or you can, you can employ millions of pigeons to get it done. It's up to you. Okay. The core idea is figure out that model that fits through the data so that we can predict better results. As simple as that. Okay. Given the past data, we have to predict the future data. Okay, that's all. And whether you use the differential, like the normal equation way, or you use curve fitting and line fitting using the gradient descent, you use decision tree, you use SVM, you use neural network, you use any other means, but purpose remains same. Okay. All right. So we learned two methods so far. One is the least squares, where dE by dm equals to 0. Other was using the gradient descent. We slowly increase error, slowly increase m, observe the impact on error, and accordingly tweak the m and c. And that's what we keep on doing. So we learned two methods so far, and we will be doing more of this in future. All right. So from here, in the next class, I would like to start with NumPy, Pandas, and also Matplotlib. Okay, I would spend some time in NumPy. The way I'm thinking is that we will do image manipulations to understand what it means by transpose, what it means by inverse of the matrix. Not inverse, we call it transpose. We'll also do some more manipulations of the data, and I'll prefer doing it using image so that you know what we're doing. Like, for example, given an image, increase its reduce its size. Okay, given an image, how would you reduce size? Given an image, how would you increase its size, like number of pixels? If you have to give in an image 10 by 10 and you have to increase its size to 20 by 20, what will you do? Okay, those kind of things we'll study as we go ahead. All right, this is fairly untraditional, and you will see that a lot of magic actually happens if you go using the first principle. Okay, so we'll continue from here in the next week at the same time. So we'll be starting with NumPy, Pandas, and Matplotlib, and a bit of linear algebra also. We have already started with the algebra and calculus, and we have also introduced you quickly to the linear algebra, but I want to do it a little bit more details from the next week onwards. All right. So have a good day, and yeah, go through this notebook. I'll just commit it before exiting the Zoom meeting. You can stay or you can drop out.
Thank you. Bye-bye.
Thank you, Sandeep.
Just committing it. Good night, guys. If you are, let me see. Okay, so I'm here. This one I did not make any modifications. This is the only thing I did.
And
Okay.
also this class recordings, I think Gajendra is uploading later, or someone in your team. Means not immediately after today. So if I want to revisit your course today, I will not be able to do it, kind of.
Okay. Yeah, it'll be great if you can remind him. I'll also remind him. Okay. So I think he's not working on the weekend. Okay. All right. I'll have to just check with him if he can. Just that I don't want to, bother him all the weekend.
Yes. Then you can send the link, the recording link or something to us also directly, I think.
Yeah. I'll try that. Okay. Okay. Thank you. We'll do that.